Hello everyone. In this video, I'd like to provide a few explanations to, arguably, one of the most counterintuitive results in all of propositional logic. That is, the truth table for the if-then logical connective. More precisely, consider the statement P implies Q, or equivalently, if P then Q, where P and Q are logical statements. Then what students are taught is this truth table. Funnily enough, the majority of this truth table is easy to understand for most students, but where the confusion arises from is this third row, which essentially asserts that false implies true is a true statement. And no wonder this stumbles people. It's certainly not something that is easily interpretable. I mean, where the heck would anyone have seen this in the real world? And so how would students seeing this for the first time even begin to understand its meaning? What I found is that it really boils down to how we interpret what true and false mean in the context of logical statements. And so hopefully, the examples that I go through in this video will help you gain a better understanding of this concept. Please enjoy the video, and thank you for watching. Let's dive into the first example. I'll start by making the claim that all pens are red, or in other words, if the object is a pen, then it is red. With this phrasing, we have a statement of the form if P then Q, and so indeed we have an if-then problem on our hands. Before filling out the truth table, I'd like to suggest a way of assigning truth values to each row. Since this is technically a claim, we should try to sample evidence that either supports or goes against the given claim. That is, the evidence we sample will be the combinations of P and Q being true or false, and we will compare those combinations, the evidence, to the original claim that all pens are red, and see whether or not they prove or disprove the claim. Here's the key part. If we are only able to find evidence that disproves the claim, then we say it's false. But in any other case, that is, even if we find evidence that doesn't disprove the claim, then we say it's true. In the first row, where P and Q are true, we are asked to sample objects that are pens, P being true, which are also colored red, Q being true. Clearly, any evidence of this form will only support the claim that all pens are red, and it certainly doesn't disprove it, and so we say it's true. In the second row, where P is true but Q is false, we are asked to sample objects that are pens, P being true, but are not colored red, Q being false. So for example, we could sample blue, yellow, or any other colored pens, so long as they're not red. It shouldn't be too hard to see that any evidence of this form would always disprove the claim that all pens are red, since we aren't allowed to sample pens that are red in the first place, and so we say it's false. Now in the third row, where P is false but Q is true, we are asked to sample objects that aren't pens, P being false, but are also colored red, Q being true. This means we could sample a red notebook, a red car, literally any object we desire, so long as it's not a pen and it's colored red. The key thing to take away from this is that any evidence we sample will never be a pen, and so it will never have any relation to claims about pens. Specifically, the evidence of a red notebook says nothing about whether a claim about pens is true or false, which is to say, the red notebook does not disprove it. In other words, since our evidence has nothing to do with pens in the first place, it has no relation to the claim whatsoever, and since it technically does not disprove the claim, we say it's true. For the very last row, consider when P and Q are false. We are asked to sample objects that are neither pens, P being false, nor colored red, Q being false. Again, we could still sample objects like notebooks, cars, or whatever, so long as they're not red now. Just like the previous case, since the evidence we sample will never be a pen, it will never have any bearing on a claim about pens. It doesn't say anything about whether it's true or false. And therefore our inability to disprove the claim with this evidence means we are left to say that the statement is true. Let's look at the second example, which would hopefully be a little bit more relatable. Suppose we are randomly chosen to sit an exam and are promised that we will pass if we study. That is, we are guaranteed that if we study for the exam, then we will pass. Notice that this statement is exactly in the form of an if-then statement, and so we could try to use this to determine the if-then truth table. Consider the case where P and Q are true. Then the statement reads as, if we study, then we will pass, which is exactly what we're guaranteed, so we write true. If P is true but Q is false, then the statement reads, if we study, then we will fail, which is exactly the opposite of what we were guaranteed, and so we write false. Now consider the case where P is false but Q is true. Then the statement now reads as, if we don't study, then we will pass. The question is this a false statement? By that, I mean, can we replace the if we don't study part of the statement with something different that obviously isn't studying and still end up with a true statement? For example, let's replace the we don't study for the exam part by the statement we randomly guess at least half the answers right. Then the entire statement now reads as, if we randomly guess at least half the answers right, then we will pass. Notice that this is absolutely a true statement, as by definition, passing an exam means scoring at least 50%, and I'm sure we can all agree that it is totally possible to score at least 50% in an exam just by pure chance. It's just very unlikely. To say that this is a false statement, you would need to argue that it is impossible to pass an exam purely by chance, which is like saying it's impossible to toss a coin and flip 10 heads in a row, which we know can be done. Great, so we've now shown that the statement can't be false, and so we can confidently say that the statement is true. Finally, what if P and Q are both false? We have that the statement reads as, if we don't study for the exam, then we will fail. And just like the previous case, we want to ask whether or not this statement is false. That is, can we rephrase or adjust the statement and arrive at something that is obviously true? This time, we'll replace we don't study by we randomly guess less than half the answers correct, so that the statement reads as, if we randomly guess less than half the answers correct, then we fail, which, just like before, is definitely a true statement and is probably even easier to imagine. Hence, we say the statement is true. This next example is tailored to those who want a purely mathematical explanation. Consider the statement, if x and y are even, then x plus y is also even. In other words, if we choose two even numbers, then their sum is also an even number. Recall that an even number is any integer that can be written as 2 times another integer. So for example, 2, 4, and -6 are even numbers. And if an integer is not even, then it is always one more than an even number, and we call these numbers odd numbers, like 3, 5, and -5. Right, so suppose P and Q are true. Then the statement reads as, if we take two even numbers, then their sum is also an even number. Is this true or false? If you think about this for a while and play around with some even numbers, you'll probably find a bunch of examples where the statement is true. For instance, 2 plus 2 is 4, and 4 plus 6 is 10. These alone show that the statement isn't false, and so therefore the statement is true, but it can actually be proven with a little bit of algebra. If x and y are both even, then x is equal to 2 times some integer, we'll call it I, and y is equal to 2 times some other integer, call it j. This alone allows us to easily calculate x plus y in terms of I and j. And the number we get at the end is 2 times I plus j, and because I plus j is clearly an integer, we see that x plus y is in fact an even number. But this is precisely what the statement says, that if x and y are even, then x plus y is also even, and so the statement is true. Now consider when p is true but q is false, so the statement reads as, if x and y are even, then x plus y is not even. We now ask ourselves, is it possible to add two even numbers and end up with an odd number? You can try as hard and for as long as you want, but I can guarantee that you'll never find two even numbers that sum to an odd number. Again, this can be proven mathematically. We know that p being true necessarily leads to x plus y being even. This is from the previous example we just worked through. But q being false asserts that x plus y is odd. However, an integer cannot be even and odd at the same time. Hence, there are no two even numbers that sum to an odd number, and so the statement is false. Now, what if p is false but q is true? Firstly, what does it mean for p to be false? Since p being true means that both x and y are even, this means that for p to be false, at least one of x or y are not even, or in other words, at least one of x or y are odd. By the way, this can be shown through an exercise using truth tables, which I highly encourage you to try out on your own. I'll give a hint. The statement x and y being even is the same as x is even and y is even. This means that the statement now reads as, if at least one of x or y are odd, then their sum is even. And so now we ask, is it possible to take two numbers, where at least one of which are odd, take their sum, and end up with an even number? If you think about this for a moment, you might realize that this is totally possible. For instance, take 3 plus 5, which equals 8. In this example, it is true that at least one of 3 or 5 are odd, yet 8 is an even number. Another example is 11 plus 1 equals 12, which again, at least one of 11 or 1 are odd, yet 12 is even. You might have already noticed that in both examples, we took the sum of exactly two odd numbers to arrive at an even number. And in fact, no matter which two odd numbers you take, their sum will always be an even number. Hence, the statement is true. And of course, for the last row, consider when p and q are false. We now know what it means for p to be false, and what it means for q to be false, that x plus y is odd, and so we can rephrase the statement as, can we choose two numbers, where at least one of them is odd, whose sum is also odd? Like before, I'd urge you to play with some numbers to arrive at your own conclusion, but regardless, you should find that, again, it is possible, as shown by these examples. The key difference between this case and the last is that now we're taking the sum of exactly one even number and one odd number. Looking to algebra again, we can see that for any two numbers we choose, where exactly one is even and one is odd, their sum is always odd. And so the statement is true. And there you go. Those are my explanations for the P implies Q truth table. Hopefully, at least one of them stuck with you. And if not, I'd recommend checking out the creators I've linked in the description, who have made fantastic videos on this same problem, and are definitely just worth checking out in general. If you did manage to walk away from this video learning something, I'd recommend looking at my other videos where I go through some closely related truth table exercises, as well as a worksheet that has exercises for you to do on your own. That's all for me. I hope you enjoyed the video, and once again, thank you for watching.